thank you for the organizers in general for inviting me to give this tutorial on this topic, which I'm very interested in. And I think that hopefully all security experts are interested in this topic. I hope you will find it interesting too. And I hope that I'll be able to, teach you some stuff which is new, because I know that everybody knows a lot about PKI. So hopefully I'll be able to give some additional perspective to this important area. Okay, so this is actually a 3-day thing, right? And today we'll talk mostly about the basics. So if you know PKI really well, maybe this is a day you can skip. So I'll introduce the stuff. I'll talk mostly about X509, the most important standard, the major practical standard in this area, and specifically about constraints in X509. So we'll talk about that too. Okay. Now, all of the material here is actually, I cover it in chapter 8 of my forthcoming textbook. So if anybody wants to take a look, it's available from my website and from ResearchGate. I see I actually forgot to put my website here, but you can find it in Google pretty easily, right? So without that, let's begin. Next day, I will be talking about revocation and also a bit about the Merkle Digest schemes, because they are used in some of these revocation mechanisms. They are also used in what I will talk about in day 3, which is certificate authority failures and the certificate transparency proposal or several variants of it. So that will be on the last day. Okay, so now let's begin with the first day, which is focusing indeed on introduction, X509, and on these certification constraints. So, we'll begin with introduction. So what are certificates, PKI, the very basics of this area, right? Well, we all know that public keys are extremely useful, right? Maybe the most exciting invention in modern cryptography, right? They're also so useful. We use them to secure web connection, for software signing against malware. They can also be used to secure messaging. All the instant messaging systems use public keys and emails. And of course, for exciting applications like cryptocurrencies, blockchains, financial cryptography, and so on. Many things. Now, the challenge is, how do we know what is the public key of an entity we are communicating with? If we received some software signed, how do we know it was actually, what was the public key that we need to use to verify it, and whose public key is it, right? So these are usually the main mechanism for us to do this is by checking the signature over the public key, and the signature are by some entities which we should trust for that purpose, which we call certificate authorities. And this issue of trust will be the main issue that we'll talk about in all of these presentations. The trust in these authorities, how do we deal if the trust is broken, and so on? How do we know if we should trust them, and so on? In particular, if we look at browsers, or more general in the TLS, SSL TLS protocol, then the browsers or any TLS SSL client maintain some list of root CAs. These are CAs that the browser kind of natively, they trust to certify public keys of different entities. So let's look at the high-level view of how does it go. And of course, again, I assume most of you guys know this very well, so I can go over it relatively quickly. But again, everybody is welcome to kind of stop me and ask questions all along, right? Okay. So we have these certificates, which are signatures by some entities, which we call the issuer or the certificate authority, over the public key of an entity we refer to as the subject. In the case of web security, this will be the website, for example. So it will be the website, for example, bob.com, right? And there could be also some additional attributes that we sign together with the public key. For example, maybe the most basic attribute which usually exists in public key certificates is an identity, an ID for the subject, the name of the subject in some way or some other identifier for the subject. And we expect the CA, the certificate authority, to actually validate this connection between the public key and these attributes, for example, the identity. There could be some potential liability for that, but we don't get into the legal question of the liability and so on. We are really focusing on the technical aspect of it. Okay, and this certificate will be used with the attributes by the relying party, in this case, for example, the client Alice, to make decisions. For example, should I use this website or should I run this software, and so on. So as we can see, the subject in some offline process in advance goes to the CA, gives its public key, the subject's public key to the CA, and as proves its own identity or any other attributes that we want to have in the certificate, and then it gets back the certificate. And when the client communicates with the subject, then the subject will send the certificate, which is a signature by the CA over the identity of the website, bob.com, over the public key, and potentially over additional information, attributes, and so on. Okay, so that's a very basic structure of public key certificates and how they are issued in a simplified way. We'll talk a bit more complex in a second. And all of that is what we call PKI, this process of doing it, right? But now that, of course, was not really defining what PKI means, just to say all of that is what we call PKI. So what really is PKI? And that actually is not a very easy question to answer. There are different kind of vague definitions. For example, let's look at actually at the kind of classical standard of PKI, which is, I'll refer to it later again, which is called X509, which was issued by ITU, International Telecommunication Union, by its technology group, and also by ANSI, later on in ISO. And they say PKI is the infrastructure established to support the issuing, revocation, and validation of public key certificates. So that is, yeah, that's pretty much true, except that it does not really tell us, because what does it mean that it is the infrastructure, right? I mean, clearly PKI stands for public key infrastructure, but what does it mean exactly? Infrastructure, it's not like a road infrastructure, which we all understand. What does it exactly mean for PKI to be the infrastructure? When can we say PKI is correct or incorrect or whatever, right? So it's not very well defined. And actually, there are a few other kind of these fuzzy definitions. For example, two different ones from NIST, which are completely different, but again, both of them are kind of fuzzy and not very clear. Now, that's a bit surprising. I mean, we all agree that PKI is a basic ingredient of modern cryptography. And modern cryptography is all about definitions and provable security and everything. Turns out that PKI is not really following this line, and we don't have, this kind of provable security. So that is actually something that I with some of my colleagues, in particular, Professor Eva Seiter from Trinity College, we are working with some students on this kind of provable security for PKI schemes. We define PKI schemes as, like every cryptographic scheme is a set of algorithms, specific set of algorithms. You can implement all of them or part of them to get all properties or some properties, like many, like other cryptographic schemes, right? And these are essentially the algorithms that the CA, certificate authorities, relying parties, and potentially other parties should use, right? So these are simply the set of algorithms that you should use for a PKI. And we have also game-based definitions for the security and for other properties of this. But I will not cover this in this tutorial, because this will go way beyond the time that we have. It's also kind of, just emerging new works that we are doing. So if you're interested, by all means, see, we have some version in ePrint. You're even more welcome to contact me, to ask me. I can give you the later version and so on. I'll be happy to discuss, but that will not be the topics that I will focus in this presentation. So in all of this tutorial, we'll actually not have a very you're well-defined, will not have proofs and so on. Our discussion will be more intuitive, unfortunately, okay? But we will cover quite a lot of stuff on the other end. There are a lot of kind of technical details that we will cover. Okay. And Pki is clearly used for these applications, which I mentioned before, for public key, in securing different public key applications. And the two main applications for which Pki is most critical are Web Pki, mainly TLS, and code or software signing. And we will really focus on Web Pki. That will be our focus. So let's talk a bit about Web Pki. Well, Web Pki is simply Pki as it is deployed for TLS SSL protocol, for browsers, and for web servers. The basic tool of Web Pki is that browsers have a list of the public keys of root CAs, which are also referred to as trust anchors. So they have this already preset public keys of trusted CAs, root CAs. And these root CAs are defined by several programs which identify which organizations should be trusted to become a root CA, should be trusted to certify public keys for different domains. And these we have 4 of these kind of programs for, I guess, for corresponding to some of the major browsers. So we have one by Google, one by Microsoft, one by Mozilla, and one by Apple. Okay, and these root CAs can also certify intermediate CAs. So in addition to the root CAs, which are defined directly by these root programs, each of the root CAs can also certify additional CAs that will also certify public keys of different websites. Okay, so not all public keys do not have to be certified directly by the root CAs. And the subjects, the website certificates are actually usually issued by these intermediate CAs. So that's a basic application for Web Pki in a very high level. And let's look at it, at how it is a typical way it is deployed. Yes, we have the root CA. It is issuing some CA to a certificate to an intermediate CA. And the intermediate CA is issuing the certificate to the website, which sent to the browser. And now the website has to send 2 certificates to the browser. The certificate that the website received from the intermediate CA, CB, that's in certificate that the bob.com received from the intermediate CA, as well as the certificate for the intermediate CA that the intermediate CA received from the root CA, right? So that's a certificate CICA, certificate to the ICA, to the intermediate CA. Okay. Yes. Okay, so that's again a very high level view of Web Pki, just so we have a bit of the language and the understanding of the architecture, which I assume most of you are familiar with actually. So I went over it pretty quickly, hope that was okay. Now, the main problem we are concerned with related to Web Pki is the concern of rogue certificates, bad certificates. And these rogue certificates are certificates which could be abused for different attacks on the web users, yes? And there are 2 basic kinds of these rogue certificates. They could be equivocating or just misleading, I would say, okay? Now, misleading certificates are certificates which are issued not for a name which belongs to a specific other organization, but somehow are misleading the users into thinking they belong to some organization when actually they belong to the attacker. We also refer these misleading certificates are also referred to sometimes as cyber squatting, because you kind of get a domain and use it kind of in a misleading way. And there's different kinds of them. All of them are really designed to mislead the end user. Okay, the most common, most successful apparently of these kind of misleading certificates are called sometimes combo certificates, because they combine a legitimate domain name like bank.com with some prefix, some addition, which many users will think it is still part of the same domain. So you could have it accounts slash bank.com or bank.accounts.com, all kind of combinations where the bottom line is from the domain name system perspective, from the technical perspective, these certificates, these domain names are not belonging to bank.com, so maybe they're free and one could get a certificate for them, one could buy them, one could get certificates for them, but actually the end users may think they belong to bank.com, so the user will be misled. Very related to this are domain name hacking, again, names which appear to be similar, but actually are different from the legitimate name. For example, account-bank.co, right? So this .co is a top-level domain, which has nothing to do with .com. And if the attacker managed to get this domain name, then they may mislead the user, although the computer will think it's a completely different domain. There's also homographic domain names, which appear visually to be very similar to legitimate domain names. For example, this PayPal.com, where the last letter L is indeed an L, versus this one, which is actually PayPi, because the last letter here is an I, not an L, just a capital I, which looks visually like an L. And there are many of these homographic attacks. Or typo squatting, where you simply get a domain name which is either a potential misspelling of the correct domain name, maybe an extra letter or maybe an incorrect C instead of a K, and so on. All of these are used for social engineering attacks on the human users. These are very important attacks, but not our focus on PKI, except for some monitoring for these misleading certificates, which we'll discuss towards the end when we discuss certificate transparency. So what do we focus on? We focus mostly on these equivocating certificates, which can be used for impersonation, but also to circumvent all kinds of name-based security mechanisms like blacklist, whitelist, the same origin policy of browsers. All of these require equivocating certificates, certificates which contain exactly the same name as a legitimate website, but were not issued for the owner of that website, were issued by some attacker, which wants to have a certificate for exactly the same name, but with a public key chosen by the attacker. Okay? So this is what we will mostly focus on, equivocating certificates. The rogue certificates we talk about will mostly be simply for a domain name which the attacker does not own, and therefore the attacker definitely should not have received a certificate for that domain name. And that's essentially what we focused on PKI, equivocating certificates with the same name as a legitimate website, but issued to the attacker, to the public key of certifying the public key of the attacker. So how do we get this kind of failures? So we are talking about this scenario where the attacker is sending or the user is trying to contact a website, for example, bob.com, and she's giving her browser, please contact bob.com. The browser is initiating this TLS connection to bob.com, and in the connection, the server is authenticated using some certificate. And now the question is, did we actually get the website from bob.com, or did we get the website from the attacker, right? Is this the web page as the user is seeing? Is it really from bob.com? And in the TLS communication, the server is identifying by a certificate, which provides the server's links together, the server domain name with the server public key, in order to prevent these kind of attacks. So what could go wrong is that this certificate is not actually a legitimate certificate, a correct certificate, but somehow certifying the public key of the attacker. So that's really what we want to know. TLS is ensuring us if the private key corresponding to the key in the certificate is not known to the attacker, then TLS, that's the job of TLS, which will not get into it. TLS will ensure us that we are ensuring the correct domain, the correct web page. But do we really know that we got the public key of the correct website of bob.com rather than the public key of the attacker? Okay. And there are different kind of attack vectors here. The first one, the most obvious one, is that the attacker actually exposed the private key of the website through cryptanalysis, through break-in, and so on. The attacker just found the real private key of Bob, right? Bob.d, the decryption private key of Bob, right? Now, Pki tries to mitigate that threat also when we identify or suspect that the certificate was exposed, the private key was exposed, then Bob should ask for the certificate to be revoked and get a new certificate. So that's potential mitigation for that. But there are additional attacks in which the attacker receives a certificate for its own attacker public key. For example, attacker can trick the CA to get to sign the certificate for Bob.com, but with the attacker's public key. Or maybe the attacker just is in collusion with the CA, and the CA intentionally issues a certificate for Bob for Bob.com, which is actually containing the public key of the attacker, because the CA is actually colluding with the attacker. Or maybe the attacker has exposed the private key of the CA, and then the attacker just signed the certificate by itself. Okay? Now, clearly, our hope is that these root programs that I mentioned, the 4 root programs by the major browsers, they should prevent all these attacks, and in particular, they should not include any rogue CA or any even negligent CA, which could be tricked in such way. So they should always include only reliable, honest CAs. But can we really trust these 4 programs, these root programs? And when we look at history, we find that there have been quite a lot of failures and these are just the major failures, major well-known failures of PKIs, of CAs, okay, where we had CAs issuing certificates not correctly. So you see, this is a long list, and of course, I don't want to waste our time, our limited time today, going over all of these. So instead, let's just focus on 1 or 2 of these cases, maybe the most recent ones, okay? So let's focus on these most recent from last year, okay? 2 cases. So the first, which are interesting special cases, okay? So we've used them as an example. The first one is blocking of Kaznet, okay? Kaznet was a root CA, which the Kazakhstan government required installation of this new root CA in all browsers distributed in Kazakhstan. Okay, so they required this new CA, but they did not get it into the root program. Instead of getting it into the root program, they actually just used the user interface in order to add it to all of the major, every browser which was distributed in Kazakhstan through at least through the ISPs. And then it was detected that this root CA was used for many the middle attacks on users. Therefore, it is actually, what does it mean? It means that this root CA actually signed certificates for different domains, essentially for every domain, but with the public key of the, well, apparently the Kazakhstan government or some agency of the Kazakhstan government, okay? And once this was detected, there was actually pretty harsh action against it, definitely by Mozilla and Google. Both of them, they not only they did not add Kazakhstan government CA to the root program, because, well, I guess the Kazakhstan government didn't even ask for it, but they actually detected it even when the user tries to install it, and they changed the software so it does not even install it. So that's a very extreme response, that the user interface is kind of designed to allow users to modify the list of root CAs. They actually disable the functionality if you want to install this particular public key of the Kazakh government. Okay. Now, anybody knows what was the Kazakhstan's government response to this? Anybody? Anybody guess? Anybody know? Before I tell it, any Kazakhstanis here? Just so I'm sure. No? Okay, I guess I'm safe then. Okay. So, okay, give you just a hint before that. The response was actually this year, 2020. No? Not a guess? No? Well, I'm not going to, because I don't want to give any spoilers, so I'll actually not give details of the exact response. So, yeah, but there was a response, yeah. Now, since I asked about Kazakhstan, oh, I guess that joke did not go through. That was a joke, right? Because that's the new Borat movie, right? That's a picture from the new Borat movie. So if you guys see the new, I guess maybe some of you guys are too, serious researchers and you didn't see the new Borat movie, I can only recommend it, and then you will see what I'm talking about. Of course, it's just a joke, guys. Don't take it too seriously, okay? And then, if we're already talking about jokes, so anybody from the United Arab Emirates here? No? It's okay, guys. No? Okay. So then I'll tell you something about another incident that involved the United Arab Emirates, okay? And involved a company there, which is called Dark Matter. And Dark Matter is a cybersecurity company in United Arab Emirates, which employs some ex-NSA employees as well as ex-NSO employees. NSO is a very well-known Israeli cybersecurity company, basically a surveillance company. They have several products allowing surveillance of course, at least they say for, legal purposes and so on, right? So they sell it to different governments. And in 2017, this company, Dark Matter from the United Arab Emirates, they got an intermediate CA certificate from one of the root CAs, which is Quo Vadis. And also they asked to be added to the root programs. Okay, so this is United Arab Emirates, and they've asked for this, and that sounds, so far, I guess it sounds fine. So how did it continue, this story? So actually they were refused. In 2018, they were refused, and even this intermediate CA was revoked by Mozilla and Google. Now, why did this happen? Why were they refused? So that's actually an interesting question, because the kind of legal basis or the policy used by these different root programs is not always so clear. And when you read this, the published statements about this, they basically say, we will do whatever we think is best to protect our users, without really getting exactly details of when would they approve and when would they not approve, right? Which I guess could be problematic at some point from the legal perspective. In any case, the reason they did not approve is apparently related to a series of articles in Reuters and the New York Times, which has been claiming that this company, Dark Matter, this United Arab Emirates company, has been developing cyber weapons against individuals, weapons that have been used to spy on iPhones, a popular chat application which was used to spy on the users, and so on. Okay, so these kind of spying operations, and therefore I guess Google and Mozilla decided they don't think that a company that is doing surveillance and spying operations on users should become a certificate authority, because then it will make it much easier for such a company to exactly do that, to become a man in the middle, and to interception and to eavesdropping and man in the middle attacks against users. Okay, so this is the kind of thing that caused a big problem, where we had to remove program organizations from the root CA, or we had to remove them from intermediate CAs and so on. So what are our goals here when we look at PKI? What do we want PKI systems intuitively to ensure? So one goal that we clearly discussed already is to have trustworthy issuers. We want our trust in Encore and root CAs, as well as intermediate CAs, to be trusted. And we definitely would like some limitations, at least on the intermediary CAs, so they cannot issue certificates for any domains, in particular domains which kind of don't belong to them, right? We'd like to have transparency so we can detect when some of these rogue certificates are issued. It will be good to be able to detect them. Yes, so it's some public log of certificates to prevent any kind of hidden certificates that are attacking users just of Kazakhstan, for instance, right? We'd like to have accountability to identify the issuer of a given certificate. So if we find a certificate which is bad by this transparency, we can know who has issued it. And that property is usually pretty easy because certificates are signed. We'd like to have a mechanism for revocation, a timely and accountable and transparent revocation mechanism. We would like to ensure non-equivocation. Every entity, one entity should have one certificate. That is a bit of simplification because some entities actually use more than one certificate, but at least we definitely don't want certificates for an entity to be issued to other entities. That becomes harder to define if you do allow multiple certificates. And one more goal, we would like to have client privacy. It seems unnecessary for the CA to know which website the client is using. Okay. So are we okay on audio? It's back. Okay, it's back. Fine. So, okay. So that was like very, very high level overview, right? Now, in the rest of today's talk, we'll mostly talk, or only talk, I guess, on X509, which is the most well-known, the major practical standard in this area of PKI. And the two other days, we'll talk about all kind of improvements and extensions, and all of them will be a kind of improvements and extensions to X509, because in practice, in the kind of applied cryptography, X509 is the name of the game for PKI. Of course, as I mentioned, with potential extensions and so on. Okay, so let's talk about X509. X509 is actually a kind of a part of a bigger effort called X500 of a global directory standard. And directory here is actually related to the basic phone book. And indeed, it was a project by the ITU, the International Telecommunication Unit, which is from the United Nations Organization of Telecommunication Units worldwide. And they issued the standard for global directory because, you know, at that time, it was kind of obvious that every phone company keeps a directory for its own country and for its own users. But what do you do when you want to have global connectivity? So let's connect all of these phone books together, one to the other, okay? Okay, I guess that's a good question here. I should get some time to answer it. Okay, and so that was an effort by the ITU, International Telecommunication Union. And the idea was, okay, instead of having one directory of each country, we'll have somehow connect them into a trusted global directory. They will be operated by this hierarchy of trustworthy telecommunication operators in each country, and then you'll have a global directory worldwide, right? You will be able to find people everywhere. And in particular, what is the phone book doing? It is binding your identifier to some attributes like your phone number, right? Or other attributes like maybe your address, right? I mean, most of us don't remember anymore what these phone books even contain, and right? So some of these are standard attributes, and one of the standard attributes was actually a public key, which they added the public key. The public keys were just invented a few years earlier, and the invented public key is one means of authentication of a user. That was kind of the basic goal of them, but still they were one of the standard attributes. And also they identify these standard identifiers for users, for entries, which we will call distinguished names. Okay. But before I continue, maybe I'll stop for a moment and just answer Victor's question, and Victor asks, can open source applications help to secure the problem of spying? And that's an interesting question. So it is very different from our topic of PKI, so I cannot spend too much time right now on it. But in general, this area of open source, I am a big believer in open source software, don't misunderstand me, but I am also a big believer in, well, let's say, in the big problem of identifying vulnerabilities by open software. Open source software is not free of vulnerabilities by any measure, okay? And therefore, if software can have vulnerabilities, by definition, it may also be possible to implement trapdoors in that software. And that's something that we as in the cryptographic community and in the security community, we are all unfortunately well aware of, that sometimes big potential attackers would actually try to influence even standards in order to implement trapdoors. And these things, as many of you know, have actually happened. So definitely doing it in open source software is definitely feasible. And in fact, there have been incidents which many of us believe may have exactly been of this sort, of intentionally introducing vulnerabilities into open source software. So I would really, I don't think that relying on open source software is a solution. One last comment about this, as I mentioned, one area I'm also very interested in is all this aspect of the human-centered cryptography, human-centered security in general. Protecting the real naive, sometimes users, and clearly it is impractical to try to protect software by open source if you try to protect the end user, because end users are not able, definitely, in fact, nobody, if you ask me, is able to validate all the open software that they use. Okay, so I'm not against open source software. I don't object also to the claims that it may provide some way to, to deter or to make it harder for attackers to introduce vulnerabilities, but it's definitely cannot be a complete solution. And actually, Victor, you're asking very good questions. Those are not exactly on our PKI topic. Your other question is, can anything be done against a state-sponsored attack? So I think that the term state-sponsored attack is sometimes used in the media as something which is meaning that this is an attack which cannot be stopped. That's not true. State-sponsored, state actors have a lot of resources. These resources definitely allow them to do a lot of stuff. They do not allow them to break unbreakable stuff. And when we are designing cryptographic mechanism well enough, they can prevent state actors, definitely. Cryptography has been, well, many state actors, the way they have been trying to fight cryptography was to prevent people from using cryptography. Cryptography can definitely be strong enough to withstand state actors, but definitely. I'm not saying yes that it will always work, because bugs may exist, vulnerabilities may exist, even protocols that we think they are provably secure. Sometimes we have a mistake, but this is a mistake in our proofs. Okay, if we will do our work properly, if we check our proofs properly, use automated tools to help us do our checks properly, and so indeed that's part of the reason that I'm a big believer in provable security, including for PKI. Okay, so then yes, our systems will be secure. It's not easy, it's not trivial, but I really don't believe we should kind of give up, and there is no reason to give up. As a person myself that has worked quite a lot on attacks, people overestimate the ease of attacking systems. Attacking is not always simple, and attacks, when you find an attack, it is usually, and actually it's a previous talk gave some excellent examples of it, many times, if you when people actually find an attack, it is actually very, very easy to fix and to prevent the attacks. Okay, so it is not that state-sponsored body can always, state actors can always win. Far, far from it. Okay, and people working these state actors are exactly concerned about some of these defense mechanisms because many times they are trying to attack systems. Okay. Okay, but let's focus please on PKI. Okay, you will have a lot of questions on PKI when they get to the interesting stuff. So let us get there. Okay, so this X509 never happened. Okay, it was too complex, too revealing, too much trust of telcos, and telcos themselves, they became less important, frankly. And but we did get one thing out of this. X509 certificates and distinguished names. So I guess these are two things, except that I'm not sure distinguished name is such a great thing, but we did get X509 certificates. This is a great thing. Okay, but let's begin with this thing that I'm less excited about, which are the distinguished names. Because whenever you hear about X509, you will see these distinguished names. So you need to understand what they are. Okay, so what are these distinguished names? Okay, the goals were very nice for distinguished name. The goals were to have an identifier which will be meaningful, will be unique, and also decentralized so that it could be given by all of these different telcos around the world. And the way to do it, they said, we'll have a sequence of keywords and a string value for each of the keywords so that we can identify each individual around the world in a unique way, in a meaningful way, okay? So by distributing this directory and the responsibility for it, we got this hierarchical distinguished name. And the keywords are these, you see here, you could have a country, locality, organization unit, common name, like, regular name. But and this was not necessarily, you could add additional keywords and you don't have strict usage rules. This hierarchy of the keywords was, you can decide on your own hierarchy. Somebody else could decide on theirs. They could also invent their own keywords, right? So this is like in a hierarchical way. So if the country US, locality New York, organization New York Police Department, organization unit Soho, and then we have a particular police officer, John Doe, right? And this is how we can write it in a kind of a textual way, distinguished name equal the sequence of key equal value, and so on. Okay, so now we got this distinguished name, not even kind of encoding the file to write them down. It's not really important. But what do we really get of this? Do we really get usable identifiers? So no, I don't think you get, because first of all, users don't know these names. Users, if they know anything, it is the domain name of the organizations that are trying to contact the bank, what they see in the browser and what they could, and sometimes they do type into the browser, which, let's be realistic. Most users rarely actually even type a domain name into the browser or a URL. That's not the common thing that end users do. End users mostly just type stuff in a search box in the browser and click on stuff. That's what users do. That's reality, okay? Internet application, on the other hand, they definitely do use domain names and URLs. And some users do understand them. I would hope that, for example, probably everybody here in the audience, they understand domain names, right? So some users do understand them. It does exist. It's not completely impossible. So let's say here we get the V, but definitely very, very few users will actually understand these distinguished names. Otherwise, I would not have to present this previous foil. Well, maybe I didn't have to present it, but I did, right? So luckily enough, from version 3 of X509, certificates also support what we call alternative names. And these include, the most important are DNS names, which are, essentially domain names like we are used to in the internet. You see this long identification, for example, certificate. In the certificate, we have this field of subject alt names, the alternative name for the subject of the certificate. And then we have this specific type, which is this DNS name, this specific alternative name. It can also allow wildcards, to support all of the subdomains of bank.com. And there are other types of alternative names, for example, emails, but really the most important one by far is DNS names. So that's really what you should remember as what are alternative names, but we will talk about them a bit more in a moment. So, and that is actually the important identifiers that we have in certificates are these alternative names, mainly for the subject, the website typically. So let's look a bit at the X509 certificates. We begin with version 1, and you can see quite a lot of fields, but they're actually all pretty simple, actually pretty trivial even, I would say. And then I'll show in a moment version 3. So in version 1, you see we have the version of the protocol, 1, I guess, the serial number of the certificate, which is an interesting small field. It contains a number which should be unique to that certificate, but it's not a consecutive number. Actually, the standard says it must be a random number in order, I believe, in order to protect the kind of business question of how many certificates did you issue, or how many did you issue today, right? Stuff like that. So it's not a sequence number. It should be actually a pseudo-random number, but of course, never repeating. Yes, never the two numbers the same for different certificates. Then we have an identifier for the signature algorithm. That's an identifier of the type object identifier. These OIDs, object identifier, are global unique identifiers used in many standards. I'm sure a lot of you are familiar with them. They're used for many different purposes. And one of the purposes is to identify different algorithms. And that's what we are using them here. So that will be, can be RSA, for example, or ECDSA or whatever. And then we have the distinguished name of the issuer of the certificate, the CA, the validity period, the period in which the certificate is valid, and the distinguished name of the subject of the website, for example, of the certificate. And for this website, we also have, of course, the public key information, which contains two subfields, the value of the public key and the algorithm of the public key, again, with an object identifier. Don't confuse with the signature. That was the signature over the certificate. And this is just the algorithm, which we have the public key here. Could be a signature algorithm, could be encryption algorithm, could be key exchange algorithm, and so on. And then at the end, we have the signature over all of these fields. So I think that's actually, you have quite a lot of these fields, but it's actually basically simple as the fields you would expect, I think. Okay. Now, if we focus on these identifiers, so we just saw in version 1, we only had these distinguished names, both for the subject and the issuer. But very quickly, people realized this is a bit problematic. In version 2, they added a field which we call just unique identifiers for the subject and the issuer. In version 3, they understood they must be more general, and then they went the whole way with it. And they invented a mechanism, a very nice mechanism, which is called extensions. I'll talk a bit more about it. I think this is actually the most beautiful thing in X509, and something that can be learned for many other standards. So this is really something good in X509, if you ask me, extensions. Some of them are defined in X509 of these extensions, others are defined separately. Every issuer could define his own extensions. In particular, we have a very important set of extensions called PKIX, which is defined by the IETF. It's what we call an extension profile, standard extension profile, which says which extensions should be in certificates, what exactly do we mean by them. Even some of the X509 extensions, they give a bit more specifics, which should be in certificates, which shouldn't be, and so on, and some additional extensions. This X509 is widely deployed, including in SSL TLS. So we'll mostly focus on the discussion will be on this PKIX extensions profile for X509. And these extensions already in X509 include the subject alt name and the issuer alt names that I already mentioned for these alternative names for issuer and for subject, including the DNS name, of course, to identify by domain name. Okay, so that's very important extension. I'll talk about a few more extensions in a moment. There's also X509 version 4. I will not cover it. As far as I know, it's not even widely deployed. And while there are some nice things there, I don't think anything really critical for us to cover. So let's focus on X509 version 3. And you see that the public key certificates are very similar to version 1. We actually have just these three additions over here at the end. All the stuff at the beginning here is just the same as version 1. Version 2, we just added these 2 fields of unique identifiers. I'm not going to talk about them. Actually, they are not even used, almost never. So that's like 2 additions in version 2, which are actually completely subsumed by the extension mechanism of version 3. And that's the only thing we added in version 3, the extensions mechanisms. But this one field is actually very large, both in its functionality and also in its size. It usually is much larger than all the other fields together in the certificate. So what is this field? And as I said, it's a great mechanism. Okay, so what is the extension mechanism? Each extension can contain 3 things. One is the extension identifier. Again, this OID, just a standard of identifying different objects, right? So you get a number for this standardization organization, you can define your own extension. And you could actually apply to ANSI, I think, and to IEEE and some others, and you could get your own OID for different purposes. And you just need to pay them, but yes, you can get your own number. And you can also, for each extension, of course, we have a name which identifies that extension. For example, the subject alt names that I already mentioned. And then for each extension, we have a value, right? For example, DNS name. DNS name equal ibm.com. That's a possible value. It actually consists of a key value and a data value, right? Well, these are only 2 fields. What is a third field? And also, what is so exciting here? These fields seem like the obvious ones, right? So nothing exciting here. So the exciting thing is the third field, which is actually just 1 bit, which is called Criticality Indicator. And that is really nice. Okay, what does it mean? Well, when we extend a certificate, we add this new field. The question is, what should a relying party do if it receives a certificate containing this field and it does not know this field? Should it use the certificate and ignore this field, or should it not use the certificate, or what should it do? And that field says it is critical. If this bit is on, it's critical. It means that the relying party, a party which receives a certificate, should not use the certificate at all if the certificate has this unknown critical extension. Because this extension could change everything. If you don't understand this extension, you could do some critical mistake in the use of this certificate. You could trust an entity you shouldn't trust, stuff like that, okay? So you could do a major error in treating this certificate if you ignore a critical extension. On the other end, if the extension is not marked as critical, if it is marked as non-critical, and there are only these 2 options, critical or non-critical, you cannot unmark, right? Every extension is either critical or non-critical. So if you mark it as non-critical, it means it's okay. You can use a certificate with this unknown extension, but you should ignore this. You should ignore it and just use the extensions that you know. That's it. That's the only thing, right? And all the standards of certificates, X509, Pki, and so on, they can define which extensions must be critical, which extension the issuer can decide if to be critical or non-critical, and each extension should never be critical, right? But that's also not in the certificate. That's in part of these specifications. Now, this mechanism is really beautiful. I really love it because it's actually really my favorite idea of X509. The other stuff in X509 is pretty trivial, but this is really beautiful. I really wish it was used in more standards. There are many standards that could really benefit from it, including TLS, for instance, right? So really important security standards don't have this feature usually, unfortunately. And this is very useful because it allows us to extend certificates, but in these 2 different ways, and both ways are very important in security. Ways in which you extend and you say, but if you don't understand my extension, don't use it at all. And ways in which you say, okay, you can just ignore what you don't understand. So that's okay. That was my favorite part of X509. From here, everything just goes downhill. Okay. Okay, so now just a bit about some of these important extensions. The first one we already mentioned, the subject alt name, or SAN, S-A-N. extension which bounds identities to the subject or the certificate instead of or in addition to the subject distinguished name field. And the same extension could contain actually multiple of these subject alternate names. The goal is again unique and meaningful names. And the most common are these DNS names, for example, a.com. And some standards, including TLS, allow wildcard domains like asterisk a.com, which is the obvious meaning, every subdomain of a.com. There could also be other forms of subject alt name like email address, IP address, URI, and some others. Okay. And similarly, we have the issuer alt name, same thing, just for the issuer, for the CA. Okay, so that's one pretty simple extension. We have another example of an extension, which is key usage and key identifier. Key is so actually different extensions, right? The key usage, which could be critical in X509 and must be critical in PKX, tells you what is the use of the public keys that you certify. Could be for encryption, could be to verify signature, could be to verify certificates, and so on. And then there's also an extension called extended key usage, which can give us additional optional use of the keys. So in addition to the basic use, you can also use the key for this additional purpose. And since it's just an additional use, then it is always marked as non-critical because, I mean, if you don't use it, don't use it. If you don't understand it, don't use it. Okay, you can still use it for the previous purpose, right? For the key usage purpose. But there's also another way of using extended key usage, which is detailed and restrictions which are related to the key usage, which then must be critical because these are restrictions. You shouldn't use this key for encrypting unless the key is, over some length or whatever. And then there is subject and authority key identifier, which allow us to identify a particular key if the subject or the CA has many keys. And that's just a bit of optimization. So, for example, when you do it for the CA, for the authority key identifier for the signer, it just means which public key should you use to verify this signature. Which public key? Well, the key that in the certificate of the CA was identified with the same key identifier, but as a subject, because it was the certificate issued to the CA. So it's a way to essentially save our time a bit. So since it's just saving our time, but we don't need to check all the public keys that we have for this entity, just one, then it's non-critical. If you don't know it, just use all of them, who cares? Another example of an extension is certificate policy extension. That's actually a slightly more interesting one, I think. It defines the policies used or set by the issuer. It should always be critical because you should always understand the policies of the issuer. And while I will not go over all the different policies, one of them is really important, which is what was the method, or how much can you trust the validation of who was the subject? And you could have your organization validated. For classical certificates, some person from the CA certificate authority checked that the subject is really the subject by looking some documents or whatever. We can have domain validated, which is this automated checks. We only sent email or sent a packet to the certified domain, to the domain that we are asking for the certificate for. When we got back the expected response, we just issued it. Domain validation is very important. Most certificates today are domain validated because of a simple thing. We don't need a person to do the check. So it is easy and quick and cheap, okay? On the other end, of course, from security perspective, that may mean also that this automated check may be something that we could circumvent. In particular, for example, Chaya, who introduced me so kindly, has actually very nice work showing how this domain validation may be, an attacker may be able to circumvent this domain validation. So this is a very dangerous mechanism. On the other hand, again, this is actually very widely used. So in fact, most certificates are domain validated. And furthermore, it's not only a question of how many certificates are domain validated, it's a question that users practically cannot differentiate between certificates which are issued in these different ways, okay? And then we have the third way, which is extended validation, which means that we can do all kind of the CA has done all kind of thorough checks, checking multiple documents, checking for a specific non-organization, so on. So these are certificates which have been checked much more. Unfortunately, the main meaning of this in reality of current PKI means that the CA received a lot more payment for them, because again, users practically cannot differentiate between all these three kinds. The kinds which domain validated, which is often completely free, organization validated, which costs you, maybe a few dozens of dollars or whatever, and this extended validation, which may cost you thousands of dollars, right? So that's really the problem. Users cannot really differentiate between them. That's an interesting subject of itself, but of course, it again falls into this issue of human-centered cryptography, not what we focus on. So that was the only comment I think I'll make on that particular issue. In any case, the policy is again identified by some object identifier, like we discussed earlier. So you have a specific number identifying your exact policy. Okay. Now, do users know which of these used and how? No, they don't know. That's the basic bottom line. Okay. So now we get to our final subject for today, which is indirect certification. Because we discussed these root CAs and we discussed intermediate CAs, but when can a CA, what is limiting anybody from becoming an intermediate CA? When do we decide that we can trust an intermediate CA? Okay. And here we have different kind of different PKI, different models of PKI models of who can certify which keys. And we are mostly focusing on this web TLS model, where we have the CAs and they're issuing some intermediate CAs, and they're issuing the certificates. There are also other models like the Web of Trust PKI, where everybody is a CA. Everybody can actually certify each other and so on. It's a graph, it's not a tree. And you could have different variants, different policies for issuing certificates. Yes. Web of Trust PKI, most well known associated with the PGP encryption mechanism, where you essentially your friends, everybody is CA, everybody can issue and certify each other. And as a CA, you certify your friends or people you know. As a subject, you can ask your friends to sign for you, to certify you. And as a reliable party, you can trust certificates from your friends. If your friends trust a certificate, maybe you can trust them because you know them and you trust them. Maybe you can also trust your friends of friends. It's up to you. It's your policy. Should you trust all of your friends? Should you trust all of them equally? These are all really questions for this model. And, not everybody would agree that you should trust all of these friends and friends of friends and so on, all these key signing parties. So this really falls into the interesting area of trust management. Whom should you trust and so on? We will not really get into this too much, okay? So let's move back, focusing on the X509 Pki. Okay, so here, and PKIX, which is using it, okay, which is providing more details. So in PKIX, in X509, we have most certificates are using these constraints on who can issue certificates and which certificates can they issue, which certificates would the relying party actually trust. So first of all, we definitely want to see that every CA was certified by somebody that we trust, ultimately getting to one of the trusted anchor or root CAs. Okay, so we ultimately want to see a path of signatures of certificates from the trusted root or trusted anchor or CA, certifying intermediate CAs 1, 2, 3, and then the subject. There must be this kind of a path. But there are also some constraints on this path, which says, would we actually accept this set of certificates for all of the certificate for all of these intermediate CAs and the certificate for the intermediate CA to the subject? Would we actually accept them as legitimate? There are several of these constraints, and they're all in extensions, okay? The first of them is an extension called basic constraints. And that extension defines two basic things. First is just a bit, is CA, is the certified entity a CA? Can we trust the certified entity to issue certificates? Is it an intermediate CA? So you see here the trusted anchor is issued the certificate to ICA1. And if this is to be held, like here, like we see here, then clearly the ECA must be true. Similarly, is when ICA1, intermediate CA1, issues certificate to ICA2, certificate to ICA2, again, ECA must be true. Otherwise, ICA2 should not have issued a certificate. And with ICA2 issued to ICA3, ECA should be true. And when ICA3 issues to the subject, then only the ECA should be false, because this is already a subject, not a CA, should not be issuing certificates. And another field in the basic constraint is path length constraint, which says the maximum number of CAs in the path. For example, in CICA1, it has to be more than 2 because we have 3 CAs here in the rest of the path. In CICA2, it has to be at least 1 because we have another CA on the path, and so on. Okay? So these are two very basic restrictions. And then we have the naming constraint, the name constraints. These are constraints on the distinguished names and on the subject alt names that could be in the certificates issued by the subject. And there are two kind of subfields of this: permit, which says we allow only subdomains of this domain, and exclude, we forbid subdomains of this domain. Okay, and then it could be again in all these intermediate certificates, we could have the same thing. To restrict further and further, only restrictions can only go, more and more restrictions on the allowed domains that we can issue. Let me give a simple example of that. So look at this figure with the different CAs here, and you see that we have some CA of global entity issuing to entity Japan, and some certificate authority for IBM issuing certificate to IBM Asia and to IBM Japan, right? But now we want some cooperation inside Japan between entity and IBM. So entity Japan is issuing a permit, a certificate with a permit certificate name constraint extension to IBM Japan, essentially saying, entity machines, you can trust certificates issued by IBM Japan as long as it is restricted to subdomains of IBM.com. And furthermore, IBM Japan can issue certificate to global IBM saying, everybody receiving my certificate should also trust certificates issued by IBM, global IBM, as long as they are in the domain of IBM.com, only restricted to IBM, and excluding, not in the subdomain JP, Japan, IBM.com, because only me should be issuing certificates for Japan. Global IBM, I don't want to trust them for issuing certificates in my domain, and so on. IBM may be issuing a certificate with exclude to the domain name IBM.com to Symantec, saying Symantec can issue certificates to the entire world, and anybody trusting my certificate is welcome to trust them, except for certificates in the domain IBM.com, because again, this is my domain. I don't want anybody to trust anybody else for that domain. Okay? So this is an example of the name constraints. Unfortunately, many of the implementations of PKI in browsers in particular don't enforce these name constraints at all, which, okay. So that concludes my presentation for today. That's a technical, more basic material on certificates. And in the next 2 days, we'll talk some much more advanced topics, which I believe this will, even people who know PKI, hopefully will learn something about revocations, a bit about Merkle Digest, because it is using some optimizations there. And that's tomorrow. And in day 3, we'll talk about CA failures and how to deal with them, in particular certificate transparency. Thank you very much.